and today we're going to be talking about different ways to solve a quadratic. The first way you probably learned to solve a quadratic was factoring, right? You have this quadratic, you know, something times x squared plus something times x plus some constant equals 0. And then you say, hey, if I can rewrite that left side as the product of two just linear things, right, then I know a product is 0 if and only if at least one of the factors is 0. So then all I got to do is say, okay, well, either the left factor is 0 or the right factor is 0, and I know how to solve a linear equation being equal to 0, since that's just solving a linear equation. So then you can easily get the two solutions to the quadratic, which may be the same, maybe one solution. But then there are two other methods, that one of which is really simpler than factoring, and the other of which is certainly more complicated. And those are the two methods that are going to work for this particular quadratic. Factoring is the one method of the three that will not work. So the quadratic we have is, and let me make sure I wrote this right, x plus, well, yeah, okay. Yeah, I think I did. X plus 3 squared equals 6. So we have, in fact, yeah, no, let me just check that. Yes, that's correct. Good. Okay. So this is actually essentially in a format that allows you to directly apply the definition of the square root, actually. The square root was defined precisely so that there is a notation for the solution to a problem like this. So this problem is in a format that is exactly what the square root, you know, the format that the square root was designed to solve. So we have x plus 3 squared equals 6. Well, the definition of the square root is x squared equals, x is the square root of y, plus or minus the square root of y, if and only if x squared equals y. A positive number x is the square root of y if and only if x squared equals y. That's just what square root means. It's like parent-child. They're inverse relationships, right? Parent-child, you know, what other inverse relationships are there? I don't know, before, after, things like that, right? X is the square root of y just means x squared equals y when x is positive. When x is negative, then x equals negative the square root of y is also the same as saying x squared equals y. Square roots are just the opposites of squares, right? That's the definition of square root. That's the key fact here. So this is, the thing is, though, is that this problem is in a format where we can use that fact about square roots to immediately get a square root notation for the solutions. Because plugging into that, that if and only if, that definition of square roots that I just gave, we have that x plus 3 squared equals 6, if and only if x plus 3 equals plus or minus the square root of 6, right? That's just applying this general rule to the case, to the special case, something squared equals 6, if and only if that thing is plus or minus the square root of 6. It doesn't matter that the something is x plus 3. This is just a variable. This is just, or rather, x is just a variable in this general rule up here. I can substitute anything into it. One important thing to learn in math is whenever you have a rule, a general rule that holds, you can substitute not only other variables into it. If the rule is for x, you can substitute t things into it, right? If you have a rule that, like the quadratic formula, if it's normally stated in terms of x, right? But if it's stated in terms of t, you know, if you state it in terms of t, it's still true. And if you even have, you know, apply it to something where you don't have a simple variable that you're plugging in, but you have some expression, that also works. So this, you know, you can plug this into it. It's still valid, right? We're saying a thing squared is another thing if and only if the first thing is one of the square roots, positive, negative of the other thing. So we can apply that to here just fine, even if one of the things is x plus 3 rather than a simple letter. Okay, so this just tells us by the definition of the square root, right, that x plus 3, if x plus 3 is plus or minus the square root of 6, then by golly, x must be a solution by the definition of the square root. But are there x's such that x plus 3 is equal to plus or minus the square root of 6? Well, sure, because if we ask for x plus 3 to be the square root of 6, then that's just a linear equation at x. Clearly, that's solved when x equals the square root of 6 minus 3, also known as negative 3 plus the square root of 6. Same thing with negative square root of 6, except we then have the minus sign. X plus 3 equals plus or minus the square root of 6. That is equivalent to saying that x is negative 3 plus or minus the square root of 6. It can be maybe a little tricky at first to work with like these plus or minus statements, but just remember they say exactly what they seem to say when you say them out loud and say plus or minus. You know, these equivalences are true, the first because of the definition of square root, and the second because you know, not because of, you know, the way to think of the second one being true is not because we're applying some special rule with how we deal with plus or minuses in equations, but just because, you know, okay, if x plus some constant is equal to plus or minus something, then surely x is going to be that constant, negative that constant, plus or minus that thing, because whether we use plus or minus, the square root, we'd have to just like subtract 3 from both sides to get x, right? So you can just see that, this gives either x equals -3 plus square root of 6 or x equals -3 minus square root of 6. Those are the two solutions, and once you get used to this, it's easy to write them in the compact way. Oh, okay, this just says x is -3 plus or minus square root of 6. So that's the simplest way to handle these problems. Whenever you have a problem, it's something squared equals something square root. That's what square root was designed for. Square root just means, it's just a notation for the solutions to this problem. It's not really deep that square root solved this. It's by definition that they solve this kind of problem. And not all quadratics are easy to write in this form, but if they're given you in this form, or it's easy to put them in this form, if we had like x plus 1 squared plus 7 equals 5, then you could subtract a constant and get it in this form easily. Anything that can be put in this form, any quadratic that can be put in this form, we can easily handle with just square roots. But there is another way to do this problem, and that is the quadratic formula. Now, I said factoring wouldn't work before, and the reason factoring doesn't work is because factoring is only helpful when the solutions are rational numbers, at least integers. In fact, if there's no coefficient on the x squared term. Yeah, the reason and the reason that is because whenever you have factoring, right? If I have a factor quadratic and I have integers as the coefficients, if I have like ax plus b times cx plus d, and that's the quadratic, right? And I set that equal to 0. Oh, lots of disappearing. Right? Then if I set each factor to 0, ax plus b equals 0, if a and b are rational, it's going to give me a rational number. I'm not going to get some irrational number from a nice linear equation like that, right? Same thing with the other factors. So if you can factor a quadratic with rational, that means fraction coefficients in the factors, you're only going to get rational solutions. But here we know they're irrational solutions. Well, how do I know -3 plus or minus square root of 6 is irrational? I could formally prove that, but basically square root of 6 is irrational. So it seems pretty likely this is irrational too, right? -3 plus or minus square root of 6 isn't going to like happen to be equal to -1/12 or something. It's just irrational. So this is a different sort of solution than you would get if you solve something by factoring. Therefore, this couldn't be also solved by factoring. You can factor it if you allow irrational coefficients, but you're not going to be able to figure out what the irrational coefficients would need to be in order to factor it. So factoring is only a very useful strategy if you can factor the quadratic into linear factors with rational coefficients. So because you can't do that here, as that would give you rational solutions and you have irrational solutions, then factoring isn't going to work. So we don't try that. Instead, we try the only other way I think that there is to solve a quadratic, simple way to solve a quadratic, which is the quadratic formula. Now, we can't apply that right away, right? Quadratic formula only works when we have something in the form a that's some number times x squared, where a is not equal to 0. If a is 0, it's just a linear equation, and we can't apply the quadratic formula. It happens not to work in that case. We divide by 0. A is x squared plus bx plus c equals 0. That's the only way in which we can, only form of the input that allows us to apply the quadratic formula. So how do we get this in that form? Well, first we expand out the left side, right? We're going to have an expanded form. That's a kind of expanded form that, the form that we have to have in order to apply the quadratic formula. So expand x plus 3 squared. You could FOIL it, but for me, I'd remember the rule for like the square of a binomial. It's the square of the first thing plus 2 times the product of the two things plus the square of the second thing, right? So sum of the two squares plus twice their product. So x squared plus 9, and then plus 2 times x times 3, which is 6 times x. Okay, that's the square. and then we're not squaring the other side, right? The other side, we're leaving it as it is. All we did is we expanded out the left side. So this is equivalent to the equation we started with. Now it's still not quite in the form that we need it to be in order to solve the quadratic, to use the quadratic formula, right? Because has a quadratic set equal to 0. That's the only form which the quadratic formula applies. It's assuming that it's in that form. If it weren't in that form, we have like four parameters, right? We need to incorporate, the coefficients on the left side and also the constant on the right side. If the formula had A, B, C, and D in it, you could write that formula. You could find one, derive it, and prove it, but it wouldn't be as nice. It's much better to just memorize one formula, or memorize a formula with only 3 variables in it, and just convert all our quadratics that we want to apply the quadratic formula to the right form, where there's 0 on the right hand side, and then apply that simpler formula. So that's what we'll do here. We'll subtract 6 from both sides to get 3. On the left side is the constant 0 on the right side. Now it's in a position where we can apply the quadratic formula. So let's do it. Well, What do we need to know to apply it? We need to know A, B, and C, but we have them right here. Everything is positive, luckily for us, no minus signs. A is 1, because there's no coefficient. That's the same as multiplying by 1. 1 is the multiplicative identity. Multiplying anything by 1 doesn't change it. B, the coefficient on x is just b. Oh, well, it's 6, but it looks like a b in my handwriting. So yes, it's 6. Okay, and c is 3. So we have plugged into the quadratic formula. I'll write that here. X equals negative b plus or minus the square root of b squared, I'll zoom in here, minus 4ac. Okay, why is that full board? I'll try that. Okay, 4ac over 2a, over 2 times a. Right, so we have this thing to discriminate here, b squared minus 4ac, take the square root of that, plus or minus b, and then all divided by 2a. That's your formula, various derivations of that, but here we can just apply it. So negative b is negative 6, plus or minus square root of b squared is 6 squared, 36, minus 4 times a times c. So 4 times a is 1, times c is 3. Okay. And then over 2 times 1 is 2 times a, because a is 1, remember. Okay. So now we'll simplify this. Negative 6, so what is 36 minus 4 times 1 times 3? 4 times 1 times 3 is 12. 36 minus 12, 2 times 12 is 24. Okay. Negative 6 plus or minus square root of 24 over 2. Now this looks sort of weird. We had a square root of 6 in the answer before. Negative 3 plus or minus square root of 6. Now we're getting a square root of 24. That's like a different square root, right? That seems like something very different. Well, let's see if we can simplify this somehow. Now, we know with fractions, right, we can always split up the numerator into 2 different terms. That works with integers. It works with just as well with irrationals and with anything we encounter in math. That's a basic property of addition. It comes from the distributive property, right, because fractions are really multiplication. This is the same as multiplying the numerator negative 6 plus or minus square root of 24 by 1/2. And we know that multiplying a sum by something is the same as multiplying each term by that thing and adding. That's the distributive property, a basic principle that we use in algebra. So yeah, what this means for fractions is just that we can split up the numerator, like let the denominator distribute to each numerator and sum the results, keeping track of minus signs, which in this case means keeping track of the plus or minus sign. So negative 6 over 2 is going to be the first term. Then when we break up the fraction like that, that's negative 3. Negative over positive, plus or minus root 24 over 2, right? But now I'm going to write root 24 as root 4 times 6. Why? You know, not just because I want to show off my multiplication skill facts, but because there is a way to rewrite some square roots in terms of other square roots. And the way is that whenever a number, an integer that is, has a factor that is a perfect square, like 4, which is 2 squared. 6 is not a perfect square, right? 24 is not a perfect square, but 4 is. It's 2 squared. Then, if we take its square root, we're able to like bring out a constant integer factor and obtain a multiple of the square root of whatever the rest of the number is. And the reasoning for that is that there's this fact that the square root of a times b is equal to the square root of a times the square root of b. Now you need to be careful about that if you take algebra 2 or pre-calculus and you're taking square roots of negative numbers, which there is a way to define. Yes, they're not real numbers, but you can create other numbers, define them that that are square roots of negative numbers. I is the square root of negative 1. Sounds ungrammatical, but it's a true statement. And when you're doing that, this rule is no longer true. You can easily get contradictions. It's a fun way to, make it seem like you broke math. This rule doesn't work, but it does work for positive numbers. So I'll just say, to remember that, I'll say for a and b positive, or 0 works too. So a and b greater than or equal to 0. Then this is true, that the square root of a product is the product of the square roots. Has a ring to it, sounds true-y, but it's actually true because the reasoning is that, okay, well, if square root of a, a lot of these rules, you want to figure out, the square root of a plus b equal to square root of a plus square root of b. That's a mistake people often make. They think you can do this for addition as well as multiplication. That's not true. And if you think about it, there's not going to be any intuition for why that should be true, because it's not true. You can think about it a little and you're like, why would that be true? I don't know. I guess maybe it's not. But this one, there's a simple argument for why it's true. And it's that, well, what does it mean for something to be the square root of something? Well, like we said at the beginning, by definition, that just means that it squares to that thing. It's the opposite of squaring. So this claim here, now, because remember, we're only claiming this is true. This claim is only being put forth in the case where A and B are non-negative. So everything's positive here, we're assuming. So when everything's positive, what does it mean for the square root of A times the square root of B to be the square root of A times B? Well, it means this claim is just saying that, so it's equivalent to saying that, again, because everything's positive, it's equivalent. We don't have to worry about the minus signs in this equivalence over here. We don't have to worry about this minus there in the plus or minus. This is equivalent to saying that square root of A times square root of B squared equals A times B. That's what it means for square root of A times square root of B to be equal to the square root of A times B, which is what this equality says, right? It's asserting that those two things are equal. Order doesn't matter when we're talking about equality. Square root of A times square root of B squared equals A times B. That's what it means to claim that square root of A times square root of B is the square root of A times B. And is this true? Well, what happens when we square the product of two square roots? Well, you could use the rule that, oh, a product of squares is the square of the products. Sure, but that's another rule that you want to make sure actually holds. And why is that true? Well, that's true because if we have a product of two things, CD squared, then we say, well, that's CD times CD, right? I'm using CD here because I want to be more general. I want to show that in general it's true that a product of two things squared is the square of the products. And because of the commutative and associative properties, it doesn't matter how we're multiplying stuff here. So we can just say, oh, that's equal to, well, that's 2C factors, 2D factors. That's scrolling Y. Okay, equals C squared times D squared. So this is true, right? And applying this general rule that the product of squares is the product, a square of a product is the product of squares, applying this to the case where we're taking a product of two square roots gives us this rule, right? The square of this product of root A and root B is going to be the product of their squares, according to this rule below, right? Letting root A be C and letting C be root A and D be root B, right? Then C squared is A and D squared is B, right? So we're able to derive this product rule for square roots from the product rule for squares, which just follows from associativity and commutativity. So that's, so this is a basic rule that's true for square roots. Again, in the positive case, we wouldn't be able to derive it in the negative case because then we couldn't make these arguments, because when we're doing this if and only if in the first step, you know, square root of AB is square root of A times square root of B, if and only if square root of A square root of B squared is AB. That would work, you know, we'd have to deal with plus or minuses still, and we'd get into problems there. The basic reason is with negatives, it's not as clear like how to choose, you know, a real, you know, a nice square root and a negative of that. The square roots are kind of more symmetric. I and minus I are like partners, the thing called conjugation, where you kind of like let them take each other's places. They're really like indistinguishable. You know, they're not like positive. It's not like positives and negatives in the real case, but they're actually like legitimately different. Anyway, for positives, this is true. This is a rule we can use. And this is the rule that lets us simplify square roots. It says whenever we have a square root, you know, we can, of a thing that you can write as a product, and we can write every integer as a product, right? We do the prime factorization. Then, you know, every positive integer, we're talking about positive integers here, we do the prime factorization, and then you can break it up into a bunch of square roots. We ask, how does that help, right? Like, you know, I could take root 6 and write it as root 2 times root 3. That doesn't help at all, right? Those are both just like ugly square roots. Now it just seems worse. We have 2 square roots instead of 1, right? Well, sometimes it is helpful because sometimes one of these factors on the right-hand side, maybe root A, is actually just an integer. And that happens, of course, if A is a perfect square, right? So if we can write something we're taking the square root of as a perfect square, A, times some other number, B, then we get to rewrite this square root as the square root of a perfect square, which is just a number, right? Times the square root of the other thing, B. And the square root of, so we get this, what we had before, which is square root of a sort of big number, is now a number times a square root of a smaller number. So if we've like reduced the thing we're taking the square root of, which is good, right? A square root of a small number seems kind of more complicated than the square root of some big number, right? And in this case, you know, because it's, you know, there are fewer things we'll have come up, right? If you have a bunch of square root of 3s to deal with, it's kind of nicer than if you have some square root of 3s and some square root of, you know, some square roots of, so square roots of 12 and square root of whatever, all kinds of things. So here we have square root of 24, and we apply this technique, we say, well, how can we write 24 as a perfect square times something else? And indeed, we can write it as 4 times 6, where 4 is a perfect square, right? First three perfect squares are 1, 4, 9, 16. Okay, so 4 is the only way to do it. 1 doesn't help us. 1 never helps with multiplication problems. It's just going to 1 times something is itself, right? That's not going to help us. But if we write it as square root of 4 times 6, then we say, okay, well, we break that up into square root of 4 times square root of 6, square root of 4, and this is all I did here, right? This is the only manipulation I did from the second line to the third line. I just broke up square root of 4 times 6 into square root of 4 times square root of 6 according to our square root product rule that we just looked at up there. I took square root of 6 out of the fraction just to make notation easier. This is a standard thing you can do in algebra. Basically, because division is sort of just like multiplication by reciprocal. We have associativity and commutativity, so it doesn't really matter, whether we multiply the square root of 6 by the square root of 4 and then divide by 2, or first divide the square root of 4 by 2 and then multiply by square root of 6. It doesn't matter ultimately because of the commutativity and associativity of multiplication, specifically associativity here. Or I guess that's commutativity too. Okay. So anyway, though, so we break up this thing, and then what do we do? Well, like I said, what we want to do is take square root of 4 and just say, hey, that's just 2. Square root of a perfect square is just 2. But now what do we have? We have a fraction, 2 over 2, right? Square root of 4 is 2 over 2. That's just 1. So we can ignore this fraction. It's a multiplier of 1. It doesn't do anything. And what we got left then is -3 plus or minus square root of 6, which is exactly what we got with the other simpler method that just used the definition of the square root. So we reviewed the 3 methods for solving quadratics here. The first being just using the definition of square roots to get the formula for the solution in terms of square roots, which works when the quadratic is given to us in a form that's either exactly the same form that occurs in the definition of square roots here, x squared equals y, something squared equals something, or it's very close to that. We can easily get it into that form. Normally you can't, right? Because normally if you have x squared plus something times x plus some constant equals 0, then okay, because you have x squared plus something times x, there's no way, it's hard to rewrite that as a square. That's what the proof of the quadratic formula is all about, fiddling with it until we can rewrite it as a square and then apply this method, right? The quadratic formula works, the proof works by basically taking a general quadratic, ax squared plus bx plus c equals 0, and monkeying with it algebraically until we get it in this form. And then we apply the simple definition of the square root method. And factoring didn't work, we said, because we realized we had irrational solutions. But then we were able to apply the quadratic formula in the standard way by, and this is the key thing to do, first rearranging the equation, expanding out, and moving the constant term to the left side so that it was in the form in which the quadratic formula applies. You can't apply it in the wrong form. It's just like if you have a program that's supposed to do something for you and you put input in inches instead of centimeters, then it won't give you the right result. So we do this, then we apply it, plug it in, and we got something that was just, it had a weird square root in it that wasn't the one we got before, but it turns out there's a way to simplify square roots, right, by using the square root product rule, which we proved from this perfect square product rule, or not perfect square, just the squaring product rule for the operation of squaring. From that, we're able to see that we can break up square roots over products. We can't do that over sums in general. The common mistake is to apply rules that work for products or division to addition and subtraction. It just doesn't work. Almost always, the rules are much more likely to work for multiplication and division than they are for addition and subtraction. These algebraic rules that you learn are. But anyway, it does work for multiplication, so we applied that. And then we were able to get the square root of 4, which is 2, to come out, and then we just ended up with a small square root of 6, which is a little nicer than square root of 24. At least it's smaller. It's considered simpler. It's the simplest form. If there's only one way to simplify a square root, if we, by pulling things out like that. We can't arrive at different answers. If we keep pulling things out until we can't pull anything out anymore, which is indeed the case now, because 6 is not divisible by any perfect square. Right, 1, no, 4 is too big. Okay, so yeah, 1, of course, is divisible by 1, but that never helps. It's not divisible by any perfect square besides 1, I should say. So we're never gonna do better, than square root of 6. We can't simplify that any further. There's only one way to simplify square root of 24 and square roots, and that's to eventually get square root of 6 times, square root of 6 times 4, which we can only do in one step in this case. square root of 6 times, times 1 half, times 2. Yeah, square root of 6 times 2. Square root of 24 is equal to square root of 6 times 2. That's the numerator. We divide it by 2 to just get square root of 6. And that gives us our other way of getting the answer. So these are general strategies you can use to deal with quadratics. Remember the techniques for simplifying square roots. That's very useful, and it's, it comes down from fundamental algebra. It's from the definition of how square roots work. It's because square roots are defined, via squaring, which is multiplication. They have this special property with multiplication that lets us simplify things. Sometimes you can't simplify it. There's no way to relate square root of 3 to square root of 2 in any nice way at all. They're just totally separate. But square root of 6 is the product of square root of 2 and square root of 3. And square root of 24 is just square root of 6 times a constant. So, there are these relationships between square roots, but these are pretty much it. Okay. Hope that was helpful. And now you can tackle other quadratic problems like this, applying these same methods.